Hi, everybody. Like you said, my name is Cameron. I'm going to start my presentation here. Might actually move my camera down just a touch here. But like you said, I'm a real-world meteorologist over here, aviation-specific meteorologist at Salt Lake, public sector. Let you fill in the blanks there on the rest of that, given the current environment that we're living in as public sector employees. So, but yeah, I've been doing that for about 2 years. I've been an operational meteorologist. The previous 6 years before that, I graduated from the University of Utah with a degree in both atmospheric science and mathematics in 2017. Before that, I had actually gone to CTI school at Mount SAC in Southern California to be an air traffic controller. I got kind of caught up in everything that happened in 2013, 2014-ish. So I just kind of decided I enjoyed my aviation weather class that I took at Mount SAC. And so I kind of decided to go that route as a backup. It was originally a backup plan. It turned into my main career path. So did that. And yeah, I've been loving life since I came over to the aviation side. While I was in school at the University of Utah, I was dispatching for a 135 operator out of Salt Lake City as well. So plenty of aviation experience. I've been on the network since I think my CID originates in 2002. So I'm a very old man in network terms these days. So, but yeah, I've been around the network since 02. So a long time. The network has been critically important to my career. I don't say that lightly. Getting a good place to practice, not only how your FAR 135s work when I was dispatching and stuff like that, but when I was going through CTI school, implementation of how the 7110 works and all that sort of stuff, and seeing how it works from both the pilot and controller side was really, really helpful to me. So I'm more than happy to give back to the community here. So I hope everybody learned something from this. I'm going to go over some just kind of basic stuff here. We're going to talk about weather basics, just stuff you would cover in like a weather 101 class. We'll go over convection. I'll talk probably at length, probably about AWC products because I'm kind of intimately familiar with them because we deal with them a lot. And then I'll go into the Q&A section and hopefully hear from you guys and some of the questions you guys have to answer. So yeah, we'll get started with weather basics here. Like I said, this is mainly going to be go over like stuff that you learn for sure in private pilot ground, but you're going to also learn about it if you're taking a weather 101 class at your local university or anything sort of like that. Just that very kind of basic overview of weather. So when we're talking about weather like that, the first thing we talk about besides like chemistry and stuff like that is the large scale circulations that we have on our planet. And as interesting as this is, my wife, she works on this exact same kind of concept, just not on planet Earth. She works on it on like Jupiter and other planets like this. But every planet has this concept of cells and circulations that develop on them. So for us on Earth here, we have 3 general circulations, the Hadley cell, the Ferrel cell, and the polar cell. And each of those is on either the north or south side, both of them, of the equator. The reason we have 3 is largely due to Coriolis force. So the Coriolis force it's not, the way it's kind of explained in the physics books in college and stuff is it's an apparent force. It's not a real force. It's just because of something that we see from our point of view being on the planet that rotates. But the idea is we're going to have deflection as we move north, and the reason, or south, the reason for this is because Newton's second law of motion, where an object in motion stays in motion, but because we're rotating, it's starting to deflect and that sort of thing. So, that's the reason primarily why we have these 3 cells instead of just one big cell. For example, the moon Titan that is around Saturn has 1 cell because it's a much smaller planetary body. And so, and their atmosphere is made of methane instead of primarily nitrogen like ours is. So, so yeah, our planet, like I said, 3 cells. The interesting thing is the mid-latitude or Ferrel cell is not really a cell that's driven by the circulations. The circulations are driven by the equator and the polar cell, the high pressure areas where stuff is falling down on the Hadley cell and the polar cell. And so the mid-latitude cell is kind of that Ferrel cell is more a result of that. But the Ferrel cell is hugely important because the Ferrel cell is what's driving weather in the mid-latitudes that we see. And so as a result of these cells, we get what we consider to be air masses. And we'll talk about that in just a minute here, but they help explain the basics ideas of how a mid-latitude cyclone works. Tropical cyclones are a little bit different than mid-latitude cyclones in that Coriolis doesn't play as much of a force as it does in the mid-latitudes. And so, that's why we get these very circular things, because they're spinning around the low pressure center, and the Coriolis force isn't causing as much of a deflection, because Coriolis force, it gets stronger as you move further and further north as the Earth curves up to the poles. So tropical cyclones don't do that. They do have, and they're not temperature difference derived either. There's no fronts in a tropical cyclone. They're really, really complex. Haycom and Holton, which is the meteorologist, if you're going to be a meteorologist, you're going to get intimately familiar with this book because you're going to use it in multiple classes. Edition number 6 is coming in a couple of years. So, but this book kind of is the basis of this, why I say it. It's a very deep calculus based dive into all of this stuff. And so, he says that the tropical cyclones are really, really much more complex than the mid-latitude cyclones. And that's very true. So talking about the air masses in general, and this is going back to Pilot 101 and stuff that you're going to go through. So the simplified model of the atmosphere, air masses can be classified by both their origination temperature and the surface type. Right. So and the interesting thing here is the Arctic air mass doesn't have a maritime thing, origination area, landmass, because the Arctic air mass is just physically so cold that it actually really can't hold that much moisture. So the difference between an Arctic air mass that originates over, say, the Arctic Ocean in Alaska and one that originates over the polar regions is really, really small. It's not really worth mentioning. And so we just say that they're continental. But your origination regions can be tropical, polar, or Arctic. And then the surface can be maritime, which is something that forms over the sea and has a lot of moisture, or continental, which forms over land, doesn't have a lot of moisture. And in the Ferrel cell, what happens is these will combine to create fronts as these air masses are moving past each other. And then this then drives what we now call the Norwegian cyclone model. It's not the only cyclone model that's out there, but it's by far the most common. It's what you're going to learn in most introductory classes and in your pilot books as you go through your ratings and stuff like that. So talking about fronts, these are just boundary or transition zones between two air masses of different densities and usually different temperatures. That's not always the case. I would argue that a dry line is in fact a front. It's a type of front. And so the temperature can be the same, but the difference is the dew point. And so thus the density of the two air masses is different. So a moving front is named according to the advancing air mass. The cold front is when we have colder air moving. Warm front is when we have warmer air moving. In the classic Norwegian model, we classify these as the cold front, the warm front, the stationary front, and the occluded front. So speaking about the Norwegian cyclone model, it's generally considered to have 4 stages. This is from a couple of textbooks that are out there, but the first stage is the stationary stage. The front is normally going to be stationary. In this diagram, they have it depicted as a cold front and a warm front that's just there. Normally in most textbooks, you're going to see it depicted as a stationary front. Either way, the idea is the same. The air masses aren't really moving all that much, and a low pressure starts developing in a spot somewhere along the front, and that's going to kick off the whole cycle as it moves through its lifetime and stuff like that. So we're normally going to be starting as some sort of stationary front and moving from there. The second stage is the developing stage where the cold front and the warm front begin to move as the surface low pressure develops. And so as the surface starts lowering in pressure, there's a lot that's going on. And normally we're going to have dynamics. And when I say dynamics, I mean the jet stream is going to start impacting the surface low pressure. Which comes first, the jet stream or the surface low pressure? Can be somewhat of a chicken and egg question. Generally, I would say the jet stream is normally what's going to drive this. As your jet stream starts moving in, the surface low pressure is going to start responding to the jet. And so it's going to start pulling up air as the jet starts moving in. But in this stage, the cold front hasn't quite caught up to the warm front. The warm front is moving, displacing cold air to the in the northern hemisphere. The warm front is going to be moving to the north, and then the cold front is going to start moving from west to the east. Generally, in the southern hemisphere, things are kind of backwards. The warm front is going to start moving south, and then the cold front is going to start moving the other direction. So yeah, I mean, that's the second stage. The third stage is when we've got a fully mature and developed system that's going to be moving. The cold front is going to start overtaking the warm front in spots. At this stage, the cold front, this is by far when the cold front is going to be at its most rigorous in stage 3 here. Normally, I would say with this stage, that's when we're going to start, depending on the time of year, of course, but that's when we're going to start seeing things like thunderstorms along the cold front, heavy precipitation, depending on where you are, strong winds ahead of the cold front, and the warm front could be producing freezing rain at this stage as well. So the third stage, the mature stage, is when really the most of the bad weather with the Norwegian cyclone model is going to be happening, as that cold front does begin to overtake the warm front. Now, when we hit that dissipating stage or stage 4, at this point, this is when we start seeing the occlusion develop. And so an occlusion is when the textbooks will describe, there's different versions of it. But the main idea of the occlusion is, right, we're going to have, so this is, I'm going to draw here, but so we've got a cold air mass here. We'll denote this with C, and then a warm air mass. We'll call this W here, but the warm air mass is going to start getting put on top as the cold air mass runs into another air mass of cold air. And so, you start looking at it. So there's cold air up here, there's cold air down here, and this warm air is getting advected over the top into the occlusion. And so that's when the system is really beginning to dissipate itself out, because the whole goal of what the atmosphere is trying to do in this cyclone model is we are taking temperature differences, because we have cold air in stage 1 up here, and then warm air down south below it. And so the whole point of the model is we're going to move the system like this to move that cold and warm air masses and mix it together. And so that's what the whole point of what the atmosphere is trying to do with this is. We're trying to solve a problem of, we have temperature differences, again, going back to our idea of the cells that are formed because we have these different cells, and we need to, the atmosphere is a body that's in equilibrium and wants to be in equilibrium. And so we need to dissipate those temperature differences, and that's what we're trying to do. And so, like I said, the fourth stage, the dissipating stage, is when the low pressure system is pulling that warm air aloft, and that's doing two things. That's cooling it down, because as we go up in height, we lose temperature on the parcel, on the cell, on the block of air, if you want to call it that. And so we're pulling that air up and cooling it down, and then we're mixing it all together with the occlusion. And so, like I said, there's a couple different ways that the textbooks will describe the occlusion. This is the classic example where it's two areas of cold air mass over a warm air mass. There is other forms of the occlusion. They're certainly a lot less common than this example here is. So And the occlusions can bring, in terms of hazards to aviation, a lot of different hazards that we will observe for aviation with the occlusion and the cold front in particular. But the warm front does bring its own set of aviation hazards out there as well that we'll talk about here in just a sec. So let's see here. So like I said, talking about aviation weather and weather aloft, one of the things that was really interesting when I was going through school for meteorology that, I had to wrap my head around is that, right, we, especially in our pilot classes and stuff like that, and in our weather 101, we generally tend to think of weather as happening like 2D, right? You think of your pre-flight weather brief. You're going to look at the NCEP map for the fronts and precipitation and stuff like that. You're going to look at winds aloft and stuff. We're looking at a lot of maps that are in 2D. We're not actually thinking of the atmosphere as an entity that's actually working in 3 dimensions to solve the problems of temperature differences and pressure differences and stuff like that. And so one of the things I tell pilot groups when they come through is, right, we have to think of the atmosphere in 3 dimensions rather than just 2, because even though, we're looking at the surface pressure map and we're thinking about it, that occlusion is bringing weather in 3 dimensions. That cold front is bringing weather in 3 dimensions. And so the system is, the atmospheric system is working in conjunction with all the elements that we see on these maps in 3 dimensions rather than 2. So, it's important to keep that in mind. So in particular with winter stuff, summer is a lot different. We'll talk about convection in a bit here, but turbulence can be something that we see both at the surface and aloft with the low pressure system. The jet is going to be somewhere, either normally your low pressure is going to be the left exit of a jet or the right entrance. And there's mathematical reasons for that, but that's generally where the low pressure is going to be. So with that left exit region of the jet, right, we can see strong shear in that portion at the flight levels. And so that can bring stuff. Thunderstorms can create transverse banding along the cold front, which is another type of turbulence that we'll see. Transverse banding. So the idea of transverse banding is when you have a thunderstorm that's really, really strong, it pushes up air. And what happens is that air, so I'll draw a diagram here, but the idea is the thunderstorm is pushing air up aloft like this. Well, that air eventually runs into the tropopause and then is going to start pushing out on the sides. And that's why we get that big anvil. And so in the anvil, you can actually run into turbulence if it's a very, very strong thunderstorm, really, really strong turbulence in the anvil as that air is pushing away. And there's a bunch of really mathematically complicated reasons that we will get some transverse banding out of thunderstorms and others won't. But the idea is when you have very, very strong thunderstorms, that you can have turbulence on the edges of it. So, that's talking about the cold front. The cold front can cause that. Even with no visible moisture, thermals can create areas of strong turbulence or low level wind shear during the summer. Strong warm temperatures can create those areas of turbulence. We talk about icing. Icing is another very real danger. When we have pilot groups come through the center, we stress to them, like, flight into known icing is a problem. Don't do it. So cold fronts can bring really strong lift, which lift is something that really enhances icing conditions. Warm fronts can bring potential for freezing rain, especially back east. This can bring moderate icing and can prevent you from getting off the ground, to be frank. And then strong or low mid-level jets can create strong icing over mountains as mountains force the air upwards, creating stronger icing conditions as well. So, like I said, think about the weather system in 3 dimensions rather than just 2. It's important. It's talking about turbulence. There's a bunch of different kinds. Where I'm at in Salt Lake, we have so many mountains and stuff like that. There's just so much turbulence we deal with. So shear turbulence seen in areas where there's strong shear present. Normally this is going to be with the jet stream or a low level jet. you generally tend to favor areas in front of the surface low. Frontal is caused by the turbulent eddies in a front. Normally, again, this is going to be a cold front. Convective, like I said, convective environment, air is rising. Again, thinking about turbulence in 3 dimensions, this can cause convective eddies and stuff like that you move through. And so, yeah, mountain wave is another type of turbulence. Like, we give this one a quote, because mountain wave is really, really weird. We'll talk about mountain wave kind of at the end here, but mountain wave is a very odd form of turbulence. We can experience the wave without actually feeling drops or jolts that you would of normal turbulence, because of the way the mountain waves form. There's different types, and depending on how the wave is propagating upward in the atmosphere, it can do different things. So mountain wave is kind of an odd case for sure. So when I'm talking to pilots, what I like I said, I have a degree in atmospheric science and math. Like, I'm a math oriented person. So the way I like to explain it is NASA has a really nice equation over here on the left that goes over the very, very basics for lift. It's a function of your wing area, the density of the atmosphere, and your velocity. And the velocity is squared. So if you were to start doing calculus stuff on that, the velocity is by far the most important component of this. And so on the right side, we have an eddy. So if you can imagine, as the wing is moving through this eddy, the speed over the wing is changing, because really this velocity here is actually a vector. And so as the wing is moving through the eddy, the wind over the wing is changing. And so the velocity relative that the airplane is experiencing, the wing is experiencing as it moves through, is increasing and decreasing. And so that's why the airplane, when it's in flight, in level flight, it's in a state of equilibrium. Lift is equal to the gravity that is pulling down on the airplane. And so when we start losing lift or gaining lift due to the eddy we're moving through, the airplane will climb and then drop. And so as it moves through that, that's why we experience those drops and jolts, because the wing is physically losing lift as it moves through the turbulence. And that's what's causing the turbulence out there. So, and again, it's in 3 dimensions. This graph on the right here is in 2 dimensions, but we have to imagine the eddy is something that's in 3 dimensions. And so the wind can be pushing down on the wing as well as just the air going over it. And so that's one of the best ways I've found to describe it. It makes the most sense when we start thinking about it in terms of aeronautics. You know, you start thinking about stall and stuff like that. You know, the wing goes out of equilibrium, and that is what is causing turbulence at the end of the day. So icing, like I said, another one, observed generally when temperatures are between 0 degrees C and minus 20 degrees C. Most of the time, you're going to run into your stronger icing in like the 0 to minus 15 temperature range. When we get from minus 15 to minus 20, that's when we start kind of dropping off pretty quick. These temperatures are where we allow the formation of supercooled droplets of water that freeze immediately on impact with the surface. In general, icing needs needs stronger lift to start pushing to moderate conditions or above. You know, thunderstorms can cause that, cold fronts, orographics. Orographics just means air is getting forced upwards due to mountains. So those are generally 3 things that are going to cause elevated icing concerns. But icing can form anytime you have a cloud that is in that 0 to minus 20 degree area. So it's interesting. We had in Salt Lake here this past winter. This was February 1st and February 2nd of this year. According to my research, it's probably about the singular most extreme, long-lasting icing event that the country has experienced since at least 2013. The SIGMET data I have goes back to 2013. I would guess there's probably been some before that, but we had 8 icing SIGMETs get issued from February 1st to February 2nd, and each SIGMET goes for 4 hours. So that was 24 hours, and we had like 9 severe icing pyreps. And so when we start looking at it, some of the ingredients we talk about, right? We have these mountains that are just to the west, or excuse me, the east of Salt Lake City here. And so these mountains are talking about the lifting mechanism. The mountains are the lifting mechanisms that's causing the air to rise to create those strong icing conditions. And so we look for winds and how strong those winds are relative to the mountains. So in this case, we have these really, really strong winds that are going perpendicular to the mountains, and that creates really strong lift because the angle matters, and being perpendicular is very not good, because then there's no dissipation of the energy, if you will, due to the angle. So being perpendicular to the mountains is causing that orographic component to really, the mountains to really push the air upwards in a rather violent fashion. And then some of the other things we look for icing, we have a zone of very high relative humidity here, the crystal growth zone, which is generally, we say, from -12 to -17 C. That's the temperatures at which ice crystals are most conductive to growth. Was really, really narrow. It wasn't very deep. And so because of that, what happens is the air can't take the humidity, because all of this water is gas and liquid at this point. So the air actually couldn't in this case take all of that water and condense it into a snowflake. And so it turned then into super cool liquid droplets that were getting violently lifted upwards. And so as the airplane started descending into Salt Lake for the arrival, they just encountered really, really strong icing conditions. And the westerlies that were really strong here lasted for nearly 24 hours. And I mean, we had 9 severe nine severe icing pyreps, which for us in Salt Lake is a lot. That's more than we get in most years, and we got it in 24 hours. So, like I said, lift is something that the books don't really talk about, but it's really, really important for icing. The stronger lift you have, the more potential for severe icing you have. And so, and like I said, icing is really, really complicated because cloud microphysics is really complicated. And that's the subject of studying what happens on the microscopic level inside clouds. And so, yeah, this was a good example. This was a fun day that we had at the center there. It was a lot of issues with this. So, the other kind of what I'll call large scale weather event that can cause issues is fog. There's a bunch of different types of fog. Radiation fog is probably about the most common. So what happens in this is just at night, the temperature of the surface cools down. It meets the dew point of the air, and then the air condenses into fog, generally really close to the surface. Advection fog, that's Frisco right there. It's when warm air is moving over a cold body. In this case, it's the Pacific Ocean off the coast of California. And that will then cool the air temperature down of the warm air until it reaches the condenses and then turns into a layer of fog or low-level stratus. Frisco's had issues with fog really bad this summer, but San Francisco is famous for this advection fog type issue. The other synoptic type fog is upslope fog. And so the idea is, again, temperature cools as you go up, as you start pulling it up. So you take air from one altitude and pull it up to another. The way the books generally describe it is 2 degrees Celsius per 1,000 feet. And so with that, as you pull that air up and it starts cooling, it eventually reaches a point where it reaches its dew point, and then it creates fog. Denver has this all the time, especially during winter. And Denver is my nightmare, but Denver gets a special kind where it freezes too. And you can talk about freezing fog at Denver, and then Buff Kit will start throwing things out there that I hate, like freezing drizzle and all that sort of stuff. So upslope fog, most common out there along the front range of the Rockies. And yeah, so talking about convection here, the FAA in their weather handbook, chapter 22.2, has a recipe for convection. You need 3 ingredients: sufficient water vapor. We just call this moisture, unstable air, and then a lifting mechanism. um, to create thunderstorms, and that's generally pretty pretty standard across the world for thunderstorms. So you know, talking about the different components, moisture, the atmosphere, you need enough moisture such that you can take a box of air. When we say parcel, meteorologists say parcel, that's what we're talking about. You can place an imaginary box and you take the air that's inside that box, and then we're going to start lifting it. We're going to start pulling it up in the atmosphere. It's going to start cooling, it's going to condense, and then it'll turn into a cloud once it condenses. Without lift, the cloud is just a thermal and eventually kind of dies down. It'll go up and just kind of stop without that condensation. So the wet adiabatic lapse rate, which is the how fast the temperature cools down inside of a cloud, essentially, is less than the environmental lapse rate around it. And then because of that, the parcel of air then becomes more buoyant than the air around it, and then it just starts going upwards and upwards until it reaches the tropopause. And so that's why moisture is really, really important. It's that lifting mechanism to create the cloud start that needs to be there. Instability, this one's a little bit more confusing. You know, it is true you need instability to create thunderstorms, but there's a difference, at least in my mind, between the instability needed for just a general thunderstorm and what the instability meteorologists start talking about. So, and I'll go through what I mean by that in just a second, but it's confusing. The general rule is you want cold air over such that once the surface parcel condenses, it will then be warmer and more buoyant than the surrounding air. Again, the wet adiabatic lapse rate is less than the environmental lapse rate. For strong convection, and this is what I'm talking about, you need a conditional stability that is generally going to be there. And so this is an example from a couple of weeks ago. I pulled out of North Carolina. Certainly in the Carolinas that day, there was convection issues, you know, Charlotte having problems and stuff like that. But the big key here is this purple line right here is showing what the surface air will do if you start pulling it upwards. And so what we mean when we say, and if you don't know what this is, this graph here on the right is what's called a skew T. It's generally the standard now for what meteorologists use. There are a couple older methods to plot the atmosphere in 2 dimensions here, where your Z dimension and your temperature dimension are plotted. But the skew T here, the purple line is the big key. And so the purple line is what the surface, what a box of air at the surface is going to do as you start pulling it up. And so when we say conditional stability, we're talking about this particular spot. Let me pull a different color here. I think blue is probably going to be better, but we're talking about this particular spot right here on the skew T, where the purple line goes underneath the red line, because the red line is your temperature, the green line is your dew point as you go up in the atmosphere. And so when that purple line goes behind the red line right there, this is when the air becomes less buoyant than the surrounding air. And so it then stops. It'll maintain its momentum as it's going up, but then once it runs out of momentum, it'll just sink back down in this case, because it's less buoyant than the air around it. And so the reason why this is really important for convection, in particular severe thunderstorms and stuff like that, is because while this is happening, the upper atmosphere is still continuing to cool and the surface temperature is continuing to warm. And so what ended up happening on this day with this skew T is this purple line got pulled out this direction. And so when we measure the energy that the system has, we want to measure the area between this purple line and the red line. And we will, how much area you have between those two is how strong, how much energy your atmosphere has. And so it's called CAPE. That value is called CAPE. And so in this particular case, as the temperature pulled up to 87 to 90 degrees, this area of instability, what we call the cap, meteorologists will often refer to this as the cap, the cap eroded. And then once the cap erodes, the parcel at the surface doesn't have any anything to stop it. And so then that's when you get your big thunderstorms and stuff. And so when you hear the SPC or your meteorologists on TV talk about the cap, that's what they're talking about. It's that stopping, the ability to stop the convection until it gets to such a point where it's going to experience explosive growth. And that's when you're going to see your severe thunderstorms and stuff like that. That cap is really, really important to, in particular, hail, really strong hail development. So yeah, like I said, the FAA mentions stability in that. It's conditional stability in this. And it's, like I said, when I talk about conditional stability, it's at a level that's a lot higher than I think what the FAA talks about, because the FAA is talking about, a small cap to, just for general thunder. But when we use that term in meteorology, we're almost exclusively talking about severe weather. So, if you're watching your local TV meteorologist and he's talking about the cap, because of severe potential, that's a sure sign that you probably, especially if you're a VFR pilot, don't want to be flying that day. Lifting, we require some sort of lifting mechanism to lift that air parcel as well. These can vary. We can have surface lows, fronts, upslopes, dry lines can also cause that. Again, talking about the difference of density of the air, outflow boundaries, local winds. Local winds is what drives Florida weather. Florida is a very, very, very unique environment, really, in the world. But the idea is we have the Florida Peninsula here. It's like that. And so what happens is there's local winds that develop called sea breezes. And so the sea breeze, because you're surrounded on this peninsula by the ocean, the sea breeze actually pushes in towards the land during the afternoon. And so once these two air masses run into each other, they don't have anywhere else to go but up. And so that's why you get development in Florida in the summer every single day without fail, because those local winds are creating a boundary that's then forcing the air up, creating that lifting mechanism that you see. So, yeah, those are kind of the ingredients that the FAA outlines we need for thunderstorms. Like I said, the atmosphere is very, very complicated. It's not super simple. So this is really simplifying it down. So, one of the things I did want to talk about, because I am a West Coast based meteorologist, is like the difference that we see in thunderstorms between East Coast thunderstorms and West Coast thunderstorms, because there is a very, very real difference. The Rocky Mountains function as a significant barrier for thunderstorms and a transition. So east of the Rockies, the moisture out of the Gulf is really unobstructed. There's nothing there to really stop it. So thunderstorms have a lot more moisture to work with, is the big thing that's the difference. So they have a lot more moisture to work with. This leads to relatively low, what are called LCLs, or lifted condensation levels. This is the level at which, again, if you take that box of air, pull it up, this is the point at which it's going to turn into a cloud. And it's really relying on your dew point. So back east, these wet microbursts and stuff are a lot more common, especially thunderstorms with large hail, tornadoes, because there's no obstructions to stop the shear, are a lot more common. Whereas west of the Rockies, on the West Coast and in the deserts, the moisture source is nowhere near as good. We're talking about Baja California pulling up from tropical systems and stuff like that. It's nowhere near as good. And so the mountains are preventing that inward push of moisture as well. And so oftentimes the cloud bases of the thunderstorms are well above 10,000 feet. And so this presents actually a very different set of issues that you'll run into compared to what you'll see back east. And so what will happen here is when the rain shaft comes down out of the thunderstorm, it will evaporate, and then there won't be anything left. But that air is then all of a sudden colder than the environmental air around it. And because it's colder, it will then accelerate toward the ground. And so we can get these really, really strong outflows. And certainly Phoenix, down in Phoenix, I mean, they're famous for their dust storms that will get kicked up because of this, because the thunderstorm is actually not producing that much rainfall out west compared to what they would be back east. And so the deserts, they have a lot of dust, and as soon as that strong wind hits them, it kicks the dust up and will form blowing dust storms and stuff like that that Phoenix will see during the summer. So when we're talking about this in this QT form, the phrase we'll use is the inverted V sounding. And so the idea is it's super simple. It's, you know, this over here on this graphic from the Weather Service in Albuquerque, which the Weather Service in Albuquerque is the experts on the monsoon. They hold workshops every year. They've produced a lot of great papers with the Climate Prediction Center, in addition to their office. And so the Weather Service in Albuquerque does a really, really good job of preparing not only the people of New Mexico, but the country for the monsoon impacts and stuff like that. But the idea is the green dew point line and the red temperature line make a V. And so that V is your telltale sign that you're going to have problems with outflows and stuff like that. And certainly that is, like I said, something very, very common out west that out east does not really ever see. It's very, very rare out east. So yeah. Thunderstorms, hazards to aviation. As this was in the news yesterday, you know, Delta 56 ran into a thunderstorm yesterday, and he had extreme turbulence. The AIM, this is straight from the AIM. Any convective SIGMET implies severe or greater turbulence, severe icing, low level wind shear. A convective SIGMET may be issued for any convective situation that the forecaster feels is hazardous to not just small planes, but all categories of aircraft. And like I said, Delta 56 was an A350, or excuse me, not an A350, an A330-900, a Neo. So he experienced severe, extreme turbulence yesterday and had 25 injuries. You know, that's the danger of thunderstorms to aviation. It can't be understated. You know, I see Aviation 101 and all these other, you know, YouTubers or influencers and stuff talking about just how scary thunderstorms are. And it's because it's true. The thunderstorm is of utmost hazards to aviation because it just brings everything that's a problem for flying can be with the thunderstorms. So, you know, when I talk to pilots, we don't mess with thunderstorms. And when I was a dispatcher at my 135, you know, I got in arguments a couple times with a couple of my pilots because they wanted to fly with minimum fuel when the TAF for Salt Lake had Victus in it. And I'm just like, guys, it's not worth it. Just get an extra 500 pounds of fuel, call it good. And, you know, if we don't need to hold, we don't need to hold. That's fine. But it's better to be safe than it is to be sorry. So, another one, a type of thunderstorm is a tropical cyclone. It's a more organized form of convection. Generally, these are going to be forming between the equator and 15 degrees north or south. These are feeding off the warm water of the ocean. Unlike normal thunderstorms, the hurricane movement is actually more in the horizontal component than regular thunderstorms are. And this leads to their well-organized structure that we see. This is a picture of Hurricane Helene from a couple of years ago, actually last year. And so the interesting thing is that horizontal component being less than a regular thunderstorm, and even though temperatures at the top of a hurricane can be very, very cold, they get a lot less lightning than regular thunderstorms do. You know, generally I don't see lightning in hurricanes till they start hitting major category with category 3 and category 4, certainly producing lightning. So, you know, and obviously hurricanes are very, very impactful for a lot of reasons. And one of the interesting things that a lot of textbooks like to talk about is the hurricane has been described, and this was from a paper in the 70s, but as a Carnot engine cycle. And the idea is the hurricane doesn't really bleed off that much energy to its surroundings. And so it can be described as nearly a perfect engine cycle movement. So, yeah. Another type of convection, and this one is really strictly a West Coast problem for the lower 48 is the Pyro Cumulus. And this is becoming in aviation, more and more of an issue over the last decade. So these are created when wildfires start burning so hot, they're burning so much material that the surface air rises to a point where it can condense, and then it will form a thunderstorm as it starts continuing to rise as the cloud. And so we can get these over fires. They will be nearly stationary. I have seen in my time in Salt Lake here that we have started seeing deviations up to like 37 or 38,000 around pyrocumuluses because they're starting to get so hot and so high. So when we talk about climate change, one of the big things with climate change is wildfire behavior in the West. In the East, it's a little bit different story. There's a lot of, again, going to the differences, there's a lot of water in the East. And so that precipitation during the summer really limits the wildfire potential. And so their wildfire season back East is really like fall and like early spring, where the trees don't have leaves or anything like that. And so the East Coast doesn't really get this problem because they don't get these big 10,000 acre wildfires that we do out West. Out West, where these wildfires are becoming stronger and stronger, this is becoming more and more of a problem because, as we'll see when the AWC talks about C-SIGs, the AWC doesn't have a method to actually cover pyrocumulus clouds. And so, as we move forward, this is going to have to be something that both the FAA and the Weather Service come to an agreement for what they want to do for the product, because it will continue to be more of an issue as we move forward in a warming climate. All right, AWC. Talking about the AWC products, the first and foremost, again, we're going to go over some basic stuff here, and then I'm going to start talking about some of the other less known stuff. The SIGMET. There's two different types of SIGMETs. I'm going to talk about the non-convective first. Generally, these are going to be issued for severe turbulence, severe icing, IFR due to blowing dust or sandstorm. Again, talk about West Coast problems. This is almost strictly a West Coast problem. That IFR dust storm that Chicago had this year was unprecedented. Again, talking about my research that I've been doing on some of these SIGMET stuff. That was the singular furthest east IFR set of SIGMETs that my data set has going back to 2013. So that was an exceptionally rare event. Normally the IFR capital of the world is down by El Paso. That's where it happens. That's where it's most common. But certainly a lot of the Western US has issues with IFR SIGMETs due to blowing dust. The big one is volcanic ash. Volcanic ash is, there's no other way to describe it. It's an extreme danger to aviation. Pilots personally can have their minimum of hundreds of miles away from the SIGMET. Dispatchers will completely avoid. The volcanic ash SIGMET product is actually really, really interesting. It doesn't actually originate from the Aviation Weather Center. It originates from the Volcanic Ash Advisory Center, or the VAAC. What happens is they'll put out the advisory, and then the AWC essentially will take that polygon, draw it in their software, and then it will convert it to the text format that the FAA uses, using VORs and radials and distances and stuff like that. And so then they'll republish that. But I personally hope that I never have to deal with volcanic ash SIGMETs in the CONUS. Stuff coming from back east, pilots still avoid it, but generally it's less intense than what we would see, for example, from Mount St. Helens. So if Mount St. Helens or Rainier, those would be the big two ones, but if either one of those two had a interruption, it would be a, first off, very busy day, but the planes will immediately ground themselves. And you'll see, the way I explain it to most people is, your pilots are going to scatter like cockroaches in the light. They're just going to, if they're in that SIGMET, they're getting down immediately and landing. If they're going somewhere in the SIGMET, they're diverting. They're just getting out of the way and not dealing with it, because VA is that dangerous to aviation. So the other SIGMET type, the convective SIGMET, These cover strictly thunderstorms. Like the FAA, the Weather Service has their own set of orders and stuff like that. This is 10-811, which defines aviation weather services. They issue them for lines of thunderstorms at least 60 miles long, with 40% of thunderstorms along its length. An area of active thunderstorms judged to have a significant impact on the aviation safety, covering at least 40% of the polygon, or embedded or severe thunderstorms expected to occur for more than 30 minutes during a valid period, regardless of the size or area. The convective SIGMET is a very, what's the word I'm looking for? It's a very, very like, it's issued at this time, and they generally don't like to issue amends or anything like that. It's not flexible. It's a very rigid product. And so the AWC issues at 55 past the hour, generally going to be valid for 2 hours. If a thunderstorm were to develop outside of this, in general, what you're going to be looking for is what's called a center weather advisory, or a CWA. And again, we talked about the convective from the AIM. A convective SIGMET can include turbulence, icing, all that bad stuff, low level wind shear inside a convective SIGMET. So you got to be careful. AIRMETs, you talk about AIRMETs, they're broken down into 3 different types. There's the Tango AIRMET, which stands for turbulence. You have high level turbulence, low level turbulence, and generally the delineator is flight level 180. Low level wind shear, gains and losses, of 20 knots, surface winds over 30 knots, and then there's a Zulu AIRMET for icing. Generally with the AWC now, with its more modern website that they've got, the freezing levels will be included in the product, in the XML file and stuff like that. There's also the polygons for moderate icing or greater, and then the Sierra IFR AIRMETs. IFR, mountain obscuration, pretty self-explanatory. So yeah, one of the interesting things is the AIRMET relationship with the C-SIG. The convective SIGMET is generally considered to be an all-inclusive and overriding product from the AWC standpoint, because it includes severe turbulence, severe icing, low-level wind shear. As such, the AWC generally does not like to put AIRMETs where they expect C-SIGs are going to be happening. And so what I would say here is that the AIM and the docs for Part 91 and stuff talk about the standard weather briefing, looking at the convective outlook and the convective outlook is issued every 55 minutes. And it covers, I think, out to 6 hours. But legally, the outlook is like the defining product that would be covering these conditions, when you're talking about the legality standpoint and stuff like that. And so the reality is, in practice, that's not what we're actually looking at. Like, for example, if you go to the AWC's website and try to find the outlook right now, it's really only available in the API. It's very, very hard to find. We can find it in the NWS software called AWIPS. But for the general pilot to find the outlook now, it's very, very hard. I don't even think I've seen it in 1-800 Weather Brief or anything like that. So, the outlook is kind of a product that I think is really going away at some point. In practice, what we actually look at is the SPC day 1. And this is, again, another product that should generally be included in your standard briefing when you're getting ready for your flight. So that generally covers the whole day. And it gives a good indication of where there's going to be strong thunderstorms and stuff like that. So in this example I have from Florida on the right, we have all these turbulence PIREPs, low level wind shear, and this sort of stuff, but there's absolutely no turbulence AIRMETs because, like I said, the AWC is considering the C-SIG and the outlook to be overriding compared to the AIRMETs. So we generally won't see the AIRMETs here with these areas of big convective SIGMETs. So next, talking about the CWSUs and the CWAs. So the CWSU stands for Center Weather Service Unit. Every Arctic except Honolulu, Guam, and San Juan have a CWSU located within the buildings. The primary product the CWSU issues that's relevant to air traffic controllers and pilots is the Center Weather Advisory. It's a short range, essentially advisory product. Generally, the CWA is going to cover developing thunderstorms where there's no C-SIG active. So as soon as I start seeing tops above 30,000 feet, that's when we're going to start, the discussion on CWA and stuff like that. After that, it kind of varies by, in the Weather Service, you refer to your SOP as an SDM or Station Duty Manual, but the SDM is going to cover what you generally are going to be issuing center weather advisories for. A lot of center weather advice, especially during the winter, a lot of CWSUs are issuing center weather advisories for areas of IFR where there is no AIRMET, maybe because it doesn't meet the threshold requirement that's defined in the AWC's directive for the AIRMET coverage. And so they'll issue a CWA for that and that sort of stuff. But with that said, the CWA, again, the NWS Directive 10803 gives the Center Weather Service units a very wide range of discretion that they have to issue the Center Weather Advisory. It can cover just about anything, even stuff that may not seem like it's that big of a deal. So, for example, it can cover low-level wind shear. It can cover strong winds and stuff like that. It can cover a lot of stuff because the directive gives the CWSUs a lot of leeway in how they're doing things. So the CWSU's other big thing that they are is, when I talk to people about it, is the CWSU is the coordinator. When we look at how the Weather Service in particular is organizing aviation weather products in their organization, there's a lot of different entities that are working on this. You have Weather Forecast Office, or WFOs, that are writing the TAFs for the local area, that are writing the AFDs, that are doing warnings to the airport operations people that are, plowing the runway and stuff like that. They have a specific warning for that as well. So they're doing that kind of thing. We have the AWC, obviously, which is doing the SIGMETs and AIRMETs for the whole country. And then if you're in Alaska, you have the AWU. This is doing the exact same thing. It stands for Alaskan Aviation Weather Unit, or AAWU. They're the exact same thing as the AWC, just for Alaska, because Alaska, like a lot of things, has their own problems that they deal with. And so it's more conductive that they have their own AWC up there, essentially. And they have their own CWSU at the center too. So, and then finally, we have another entity of Weather Service personnel called the National Aviation Meteorologists. These are, or NAMs, as we refer to them. These are meteorologists that are based at the FAA Command Center in Warrenton, Virginia. They assist the traffic planners, the TMOs, everybody over there with TMOs, the NOMs, the national operations managers, with not only what's happening that day, but the next 2 to 3 days. And obviously the command center will be the liaison between not only all the centers, but also the airlines themselves and all that sort of stuff. And so, like I said, the National Aviation Meteorologists. And so the CWSUs, where they come in, is you are going to coordinate with all of these entities to provide a uniform message to the FAA at the center. And so the CWSUs will coordinate on TAFs. They'll coordinate on AIRMETs and SIGMETs. Generally, the Aviation Weather Center will not issue a SIGMET for non-convective reasons. Convective SIGMETs, they'll do it. They just kind of do it without coordinating because, for the most part, it's fairly obvious. The CWSU is issuing CWA and all that sort of stuff. So, but non-convective SIGMETs, the AWC almost across the board won't issue a SIGMET without talking to the Center Weather Service unit first. And then the Center Weather Service unit will also communicate their issues that they think they're going to have through PERDI and stuff like that to the National Aviation Meteorologist at the command center. And so everybody is talking to the CWSU, and so the CWSU can sit there and be like, okay, maybe that, for example, maybe the WFO has low level wind shear in the TAF for O'Hare, but the AWC doesn't have a AIRMET out for low level wind shear. The CWSU can, talk to the WFO, talk to the AWC, and bring everything in line. So that way, when they present it to the FAA, when everything gets published to awc.gov or to your ForeFlight app through the TAF, everything is in uniform shape and across the board, because you don't want scenarios where different entities within the same organization are saying the same thing. And there's really a big push, and I'll talk about it here at the end, in the meteorology community, talking about social science and the idea of unified messaging. And so, like I said, I'll talk about that in a little bit, but the CWSU is a very, very important entity in the aviation weather system for our country in the public sector. So talking about the CWSUs again, I'm like I said, I'm out west. Mountain waves are a really, really odd quirk of like the aviation weather product suite. Like I said earlier, they may not actually necessarily be turbulence in the traditional sense. This word laminar flow just means smooth flow. And so because of the smooth flow, turbulence may not actually be observed, but this doesn't mean that it's not a danger to aviation. Like in particular, you talk about, and this is good that we had Flight FX release the Citation 750 just recently. Like, you know, those C750s can be up there in that coffin corner area, you know, and so the mountain wave can be a really dangerous thing up there. So when you have plus or minus 20 knots at coffin corner, you know, you could very easily start going into stall speeds and have to descend to keep yourself out of stall. And so it can be a dangerous place. In addition to the low level airplanes that are flying over it at the just above ridgetop level, they can see the same thing. So, like I said, mountain wave is generally seen in two areas. You see it close to the ground at the top of the ridgetop level. As that air is accelerating over the top of the ridge, you can have decreases in speed. Generally, I'm going to try to draw a diagram here, but generally mountain waves. So let's say we have these mountains like this, and then we have the wave, which I'll draw in black here. So generally what happens with the wave is it's going to propagate upwards through the atmosphere to the flight levels. And so we run into two areas where there are problems. And so the first area is down here at the ridgetop level, where we have stronger winds going over this. And generally this is an issue for smaller planes, your Cessnas, your Pipers, your stuff like that, you know, the altitude over the ridgetop can be an issue. So that's number one. And then number two is at the flight levels. And there's certain conditions to this where, you know, depending on the shape of this black line, we can get different types of turbulence. And so, the mid levels in general actually are pretty smooth with any sort of mountain wave. You're not going to really see all that much there. And certainly the SIGMETs generally don't tend to go down into the flight level 200 to like 180 range. So yeah. Again, West Coast versus East Coast. East Coast has relatively few mountains. I have seen some of the East Coast Center Weather Service units freak out when they start getting plus or minus 15, whereas out west, if you get plus or minus 15, it's like you're barely getting out of bed type thing. 25 is the threshold where you start having problems. But the NTSB is so concerned about mountain wave that they actually have a letter written in, I believe, 2019. This letter was written to the FAA asking for the FAA and the Weather Service to come to an agreement to create a new AIRMET Tango category for mountain waves. So, you know, like I said, mountain wave is a really, really odd one. Every pilot that I talk to about mountain waves because, you know, we just don't, sometimes you don't, especially if you're an East Coast based pilot, you don't think about it that often. Some of the other things the AWC does, the TCF, traffic flow, it's an acronym within an acronym. It's horrible. I hate it. But this is just basically a forecast for 4, 6, and 8 hours of where thunderstorms are going to be covered. If you see a purple line like we did this day on the 24th of July in Minneapolis, actually that was the 23rd. It was the 24th 01Z. So the afternoon of the 23rd. You know, that's basically what that means for the traffic managers is that's an impenetrable line. We're going to need to be routing airplanes around it. Maybe we need to start thinking about some routing structure and stuff like that. Some other TMU stuff. So, you know, this is another thing that not only the CWSUs do, but actually all the airlines too as well, where the airline meteorologist will actually chime in. We have a chat through NWS chat that where everybody will chime in and talk about these products and, um, you know, what we think needs to be done, any changes and stuff like that. So, again, going back to social science, right? The academic community of meteorology is really honed on message in the last decade. So when we have public and private entities that are combining to create a unified forecast, the users are much more likely to take heed of that and take that into consideration. So you can see there's different coverage categories. There's sparse, medium, and solid coverage when we're doing this. So yeah. International tropical SIGMETs for my New York folks, Miami folks, and Oakland people in here. These are the SIGMETs that are covered, the oceanic areas. Tropical storm SIGMETs are international SIGMETs as well. They're almost the exact same criteria, but we do have different offices. So the WFO in Honolulu covers like Guam and a lot of this stuff that's to the south and to the west of Honolulu. So there is different offices that'll do that. But again, they're the exact same things as regular SIGMETs in the CONUS, just different in how they're issued. Like I said, the future of forecasting that the social science has really started to key in on in the last decade for meteorologists, and this is especially for a lot of the old timers, this is something that's kind of difficult for them to get past. But as we have these technological and computing resources progress, we have more ability to run weather models. And we're collaborating now with the social science people about how to best communicate these forecasts. And so the atmosphere, I didn't really talk about it at the beginning, but it's a very, very chaotic, and there's mathematical definitions to that I won't go into, but it's a very, very chaotic entity, and it relies heavily on the initial conditions. So how the weather model is starting, how it sees the temperatures, how it sees the pressures in the grids when they're starting. And so the academic community has really started to coalesce around the idea of we actually want to be forecasting in terms of probabilities of certain events happening and stuff like that. And so we can talk about the range of outcomes and how probable something is. So for aviation, this is a really, really unique problem because the TAF is a very rigid format. We call it deterministic, but the TAF is a very deterministic forecast. At 0Z, winds are going to switch to 130 at 11 with showers in the area and stuff like that. Like it doesn't really allow for this range of outcomes that the Weather Service is really keying in on in their recent changes that they're going through. And so the NWS has brought back the Prob 30 category to the TAF in the last year. And so that's one of the things that they can do to change that stuff. And so here's good old Denver with the Prob 30 for thunderstorms and rain showers. My guys who are at Denver, you know how tough it's been this summer. No good. But the Weather Service also has the AFD, which is a textual explanation. Again, when you're going through private and stuff like that, you'll look at AFDs. And so the textual explanation from the aviation forecaster is really you're starting to see a lot more offices go into this probabilistic stuff, talking about probabilities and stuff like that. And so that really is the future. I think ICAO at some point in my lifetime is probably going to have a reckoning with this. Certainly from the EU countries, if not the Canada. It's not NAV Canada. I forget what Canada's meteorological agency is called, but from NAV Canada and the meteorological agency up there and the Weather Service about how are we going to make the TAF more probabilistic of a format. And so that's going to come at some point. I think it's an inevitability because the academic has coalesced around this idea so fast that I think it's just inevitable at this point. So yeah, that's what I've got. I'm hoping for Q&A. I'll be here till 8:00 to answer any questions anybody has, even if we, stop the recording. I did have a few that got in line first, so I'm going to go through those and talk about some of those really quick, but I do want to hear from all of you guys. So Sebastian in the Discord asked, how reliable is radar? What are some common reasons it's not accurate? Generally, I say reliable radar is very reliable. There are a few things that we do need to consider. Again, out west, we have these coverage gaps that back east doesn't have. So this map on the bottom right here is from what's called COSPA, which is a aviation weather product from the Massachusetts Institute of Technology. And so this is showing radar coverage. So the light gray areas are where there's no radar coverage below. I think the number is like 10 or 15,000 feet, something like that. So of course, back east, we don't have any of those medium gray spots. There's nothing. It's all fine and dandy. Whereas once you get west of Denver, you start seeing these big holes in the radar coverage and stuff like that. So that's one thing to consider. Like I said, being out west, I'm intimately familiar with this. Just because you see a yellow dot doesn't mean that it's not all that bad. It depends on where it is relative to the radar, and your meteorologist will know that and sort of stuff. So you can also get ground clutter that'll get picked up due to inversions as something that can happen. Beam attenuation. So this picture in the middle here is an example of beam attenuation. So in this, you can see that the beam of the radar on this really strong line of this really strong line of thunderstorms is picking up really strong precipitation along the line before it gets to the radar. But as it moves over the radar, that line is still here, but because it's raining so hard over the radar is actually losing its ability to see past the rain. And so that can be something that can happen that you need to be looking out for. If you start talking about GA pilots and stuff like that, Sirius XM and other commercial providers, they can lag behind when the Weather Service gets the scan into their AWIP software. And so, sometimes that could be 5 minutes, sometimes it can be sooner, but that next rad picture that you're seeing on your G1000 may not actually be as it's presently happening. It may have been 5 minutes in the past. And certainly with convection, thunderstorm stuff can change very, very fast. So it's generally reliable, but there are a few things you kind of need to watch out for. Aria asked, what does pilot reporting and logging system look like? How detailed do PIREPs need to be? I tell this to everybody. There are no bad PIREPs. Every PIREP is valuable. Now, there's definitions of the 7110. In particular, it's talking about Chapter 2. You talk about Chapter 2.221. The ATC system exists to provide the safe and efficient flow of traffic. And part of that efficient and safe flow is priorities, right? And stuff. And so, the PIREP requirements are kind of can be down on the lower end of the priority for controllers. But 7110 2-6-2 lays out when they are required to see them. The 5 and 5 requirement stands for 5,000 feet ceilings and 5 miles. Icing, turbulence, wind shear, or braking action can be a PIREP as well. We've come a long way in a decade, a really, really long way. To be honest with you, it used to be, in the 2000s, we were really limited to, or alternatively, if you're a military person, the AIRMET system. I wish AIRMETs would go away. If I never had to see one again, I would be happy, but that's kind of wishful thinking. But nowadays, there's a lot of platforms to submit them. You have the AWC. You can submit one if you have your account set up at the AWC properly. You can submit a PIREP through the AWC. You can submit it still through Acer. To be honest with you, only Mastersys like Acer these days. I hate dealing with Acer. I wish it would go away. Doesn't work with Chrome. I have to go to Explorer. It's awful. SkyPath. SkyPath is, if you don't know what SkyPath is very, very revolutionary technology. And SkyPath isn't the only company that's doing it, but the idea is with the EFB now in the cockpit with the iPad has an accelerometer. So the iPad can measure and classify turbulence as it's happening. And then in turn, because everything's on the internet now or on 5G, it then peer shares that with all of the other stuff on it. So like I said, there's a few different entities that are doing this. SkyPath is probably the one that's about the most common these days that you'll hear about. But I would guess ForeFlight's going to have that pretty soon, and all these other entities too, because that social sharing of the turbulence stuff is really revolutionary. And so SkyPath, not only can it do that, but it also has the ability to generate a PyRep and stuff like that. And you'll see them. There'll be a remark in there that say generated by SkyPath. ForeFlight, same thing. There's a lot of ways to do PyReps nowadays. We're not just limited to Acer like we were in 2005. In terms of logging them, most of the time these days, I'm looking at the GFA ob map or NWS chat 2.0, because most of the CWSUs in their chat rooms, they have PyReps for the states that they cover automatically log in there. So you'll get a notification anytime there's one that's done in there. So Julian asks, what's the difference between towering cumulus and cumulonimbus clouds? And what is the best decision to make if we see them in the METAR at our destination in the simulator? So the AMS has a what I'll call rather lacking definition here, but generally the TCU is considered to be in the development stage of thunderstorms. This is where the height is much bigger than the base of the cloud. The way it was explained to me when I was a freshman is you're looking for when the height is three times as big as the base. That's when you've got a towering cumulus compared to just regular cumulus. So that's a pretty good definition right there. The CB or cumulonimbus is a fully developed, mature thunderstorm. You have to have an active downdraft with the stage, and generally it'll be generating lightning with it. How the sim handles this is an interesting topic to talk about, because the sim, we have differences between X-Plane and Flight Sim. So Flight Sim, they use a company called Meteo Blue. That's their contractor for weather. And my best guess is Meteo Blue is likely blending a numerical weather prediction model, so a global weather model, with the METARs to create the present weather. They're going to lean heavily towards the METAR when you have high METAR densities like we do in the United States. But like, for example, somewhere in Africa, you're going to lean maybe a little bit more into the computer generated model to create the thunderstorms and stuff like that. And so, like I said, the Meteo Blue is almost assuredly looking for that TS in the METAR in the US to create the thunderstorm as it's being displayed in the sim. And because they have to cover the whole world, Meteo Blue is almost assuredly using a global weather model, and that is what gives rise to some of the sim oddities that we see, because global weather models generally tend to run at 13 to 32 kilometer grid spacing. And so, actually, I think the EC is at 9 these days, but generally we're talking about 9 kilometers. Most thunderstorms are smaller than 9 kilometers in diameter. So the weather model won't actually simulate the thunderstorm because it can't resolve the thunderstorm. And so what the global weather models will do is they'll run a quick and dirty calculation for probability of thunderstorms and spit that out. And so what Meteo Blue is doing is looking at that, and every sim generates it differently, is how it's doing that sort of stuff. So that's why your buddy will have thunderstorms, but you won't. Jonah asked, we're talking about monsoon here again. Why do thunderstorms in the Intermountain West often form in the afternoons in summer? This is because we have the summertime monsoon. Monsoon is defined as a persistent change in winds. And so generally we say that winds in the Western United States are out of the west to northwest. And so our monsoon is when we get high pressure over the Four Corners area. And then this creates a more southerly wind over a lot of the or southwesterly wind over the Intermountain West. And this will then create thunderstorms. As around this circulation, what you'll start seeing is moisture will start getting pulled from the Gulf of California up into the Intermountain West. And that's why we get these thunderstorms that are developing out here this time of year. Now, this year's monsoon has been very, very different because this high pressure has been shifted much further east. I'm sure if you're here in Mississippi, you know how hot it has been the last 2 weeks. That's because this high pressure has significantly shifted. And so a lot of these deserts in California and Utah and Arizona are not getting the precipitation that they normally would be this time of year because of that. And so another result is that, again, Denver is just now right where that axis of moisture is going. And so Denver is getting slammed every single day with thunderstorms. And so, yeah, when you're looking at predictive tools for this, the best thing you can do is meteorologists. We have a tool called BuffKit. BuffKit is a software that takes the weather model and creates a simulated skew T of what it looks like. And so again, I showed you BuffKit on that icing slide. So when we go back and we look at BuffKit, there's winds and we can see the direction and the speed. And so that will inform us like what direction the thunderstorms are going to be drifting and all that sort of stuff. The real question for monsoon is exactly where these thunderstorms will develop. Generally, you have a good idea of the general areas, but exactly where, down to the right mile is insanely hard to predict. So, yeah. And I think that is all that I have for the Q&As that were done beforehand. If anybody has anything, I think we can start opening it up here. Yeah, so Honolulu is an interesting one because they don't have their own AWC. The forecasts are actually written by forecasters at the Weather Forecast Office down there in Honolulu. And so when we look at Honolulu and some of the stuff that's going out there, they won't have anything under AIRMETs because AIRMETs there's technical reasons that have to do with what's called the WMO header. I'm not going to go into that too terribly much, but for example, these hopefully there's a SIGMET down here somewhere, as I don't have my SIGMETs on for some reason. Yep, so there. So Honolulu is issuing everything underneath the tropical SIGMET header. Like I said, that's really in the weeds stuff. You're never going to see a VOR off any of this sort of stuff. It's always going to be lat longs and stuff like that. And so, but in terms of like how it realistically differs from the Aviation Weather Center product, it doesn't really differ. They're just issued by a different office. Again, you can start talking about how their SOPs differ from the AWC's SOPs and stuff like that. And that's where you're going to start seeing some of these differences. They may wait until they have one or two turbulence PIREPs, whereas the AWC is much more likely to pull it quicker and that sort of stuff. But yeah, it's not really all that different. It's just their SOP is different than the AWC's is what I would say the biggest thing is.
And folks, you are able to request permission to speak should you like to. We do have another question from Harry. How are we going to use the 1, 2, 3 rule with a probabilistic forecast?
I'm assuming. Remind me what we're talking about, the 1 mile visibility and that sort of stuff. Again, it's been a while since I've been through this, but yeah, talking about how you're going to start talking about go no go decisions and certainly alternate decisions and stuff like that with the probabilistic forecast. That's a question for the FAA to figure out what they want to do legally, because they're the legal entity that enforces the legalities of flight in the country. And so they'll come up with their own set of stuff like that. Generally most op specs, which is the airline's operating procedures, are going to say that, when we have this in a Victus, or like Victus is one of my big things I hate when there's Victus for like 5 or 6 hours. Like, come on, guys, pick a time and go with it. We have tools to narrow it down, but your Victus or your Prop 30 for TS, those generally are the overlying, like, you need to plan for the worst case scenario. And again, if your worst case scenario is not panning out, you had a little bit of extra gas, maybe you paid a little bit more, but that's going to become the price of being safer, if you will. And so, when we start talking about how they're going to, the FAA is going to implement that's for the FAA to figure out with their regulations. But the probabilistic stuff, as the pilot, you're going to see, there's a 10% probability of thunderstorms. Maybe I need to call my dispatcher, get an extra 1,000 pounds of fuel, something like that, just in case. to make you feel safer as the pilot in command for that flight. And certainly for the dispatchers that are in the chat too, right? You're a part of this process as well. And so, you have operational control over that flight. And so, you can be like, hey, there's a prob 10, so a 10% probability of thunderstorms. What do we think about getting a little bit of extra gas, probing your pilot, coming to an agreement on how to operate the flight and stuff like that. But, with the probabilistic stuff, it's coming. It's just a matter of time. The FAA needs to figure out what they want to do with it. But the social science, and there's numerous papers. I get papers in my email, once a month talking about social science stuff. Like, the social science says that users make better decisions when they have probabilities involved. And so that will apply to aviation when ICAO starts investigating it and spending money on it. And so, when you as the pilot or the dispatcher have that probabilities of what the different outcomes are, you have a better picture of how the atmosphere is going to perform. You have a better picture of the threats you need to prepare yourself for and all that sort of stuff. So, whereas the deterministic, we're saying yes, no. We miss things. It happens. It's better to be prepared with the lower end probabilities.
Okay. Harry, we hope that answered your question there. And we have Spot here who has a question. Spot, hello? Maybe your microphone thing. We'll move on to Tyler from ZTL. They ask, throughout the presentation, you've mentioned a lot of software, which, as far as I can Google, seems to be NWS internal. In the context of flight simulation, preferably inexpensive and not restricted access like FAA data, where is the best place to access forecast products, whether that is direct from AWC or not?
Yeah, so there's a couple options. So obviously we have the AWC website. Like, the GFA here can do, we'll pull this over here actually. The GFA can do a lot of things in there. And so, some of the examples that we talk about, right, is, let's see, we can pull up winds. You can pull up the ceiling and visibility forecast out here. You can actually even pull up density altitude, if you can believe it. Under the ceilings and visibility. Why it's there, I don't know, but you can do that. So they have a lot of stuff that's here. You can look at thunderstorms, where the coverage is. You talk about that TCF, that TCF's here in the decision imagery support tools that's out here. Like, a lot of people don't realize how much stuff is actually in the aviationweather.gov website, and you can get there and look at all of this stuff. You talk about radar. Okay, there's not really good software. Certainly the most common commercial software out there is called GR2 Analyst. It's expensive, but it's very, very good. But you can get a good idea of the thunderstorms using the AWC's website or weather.gov. Weather.gov has things for radar as well. But the interesting thing for us simmers is Navigraph has all of this in here. A lot of people don't realize it, but under this weather category up here, you can pull up just about everything that's on aviationweather.gov. So you can, I think even some other stuff like smoke that it can pull up and stuff like that. So let's see here. If we go to layers down here, we can change. So we can pull up, we can pull up wind barbs. We can pull up jet streams. There's so much stuff that you can pull up in Navigraph because, again, this is all coming from essentially the AWC, and Jepson is pulling it. ForeFlight is pulling it, all of this stuff. And so because Jep is pulling this stuff as well, Navigraph is pulling this in as well and putting this out there. And you can see all of this on Navigraph if you know where to look and go into it. And so I encourage all of you guys as simmers to look at what the Navigraph is doing. See what the upper level winds are doing. See what the surface visibilities are doing and all all that sort of stuff that's out there, because it is in Navigraph in your app. And so you can go in and look at it for that. But if you don't have Navigraph, like I said, aviationweather.gov, especially for us in VATUSA, has a lot of stuff in there that you can go through and do. You just need to take some time, play with it, and do all that stuff. And you don't need a pilot's license like you do for 1-800-weather brief or any of those other sort of things. So there's a lot of stuff that you can do with just those two resources that are relatively either free or inexpensive. And that's why this potential JEP sale is potentially so impactful, because, you know, Navigraph has all this stuff. And, you know, if Navigraph gets cut off from JEP because JEP raises their price on them, you know, there's going to be, there probably will be a big impact to simmers with that.
Perfect. Spot, can you try now?
Can you guys hear me?
We can hear you.
Yep.
I'd like to thanks for the opportunity here. I am a 737 captain from Brazil, and this has been a great presentation. So I'd like to congratulate Cameron for doing and thanking. It was very, very helpful. And I got a question about the Prop 30 that you mentioned earlier. I had a very, very old meteorology teacher of mine back when I was doing my private lesson, and he used to say, when you see Prop 30, you can regard it as nothing. That was like 20 years ago. How do you react when you see a Prop 30 nowadays?
Yeah, and like I said, that's the difference between where we were 30 years ago and where we are now. Like I said, the academic community has really coalesced in on that. And so, you know, for us, when I'm coordinating on a TAF with one of the forecast office, I'm talking about Prop 30. So, for example, Bozeman the other day was firmly kind of in the potential for really strong thunderstorms the other day. And so, you know, the WFO that was writing the TAF, they had Prop 30 in it and all that sort of stuff. And, you know, from where I stood, like I knew Bozeman was going to get thunderstorms. They were going to have problems. But there was indications that there was potential for hail. And so I had them amend the Prop 30 to be, you know, advertising that, hey, we have potential for hail. And that's, as the pilot, right? You know, you see that Prop 30 with the TSRA-GR, you're sitting, all of a sudden you're like, whoa, TSRA-GR, you know, we need to be on alert for that. And so some of the commercial providers that don't have their TAFs go out to everybody through aviationweather.gov. So, you know, most airlines, right, you have your own meteorologists that are in your operation command center. So for the US, American, Delta, United, and Southwest all have their own, and JetBlue, meteorologists that are based in their operation centers at HQ, working with the dispatchers, working with the traffic planners, and stuff like that, the flight planners and stuff. And so those meteorologists have the ability to change their probs, so they can do like Prop 10 or Prop 20 or Prop 30 if they want, because, you know, their product isn't going out to everybody. It's only going out to the pilots that are in the company. And so they can convey those low level probabilities that's, for example, say the Weather Service can't. And so, you know, the Prop 30 category is going to become more important. You know, that old mindset, like you said, of you disregard the Prop 30. I'd advise all pilots to not disregard Prop 30. Treat it like a tempo, because it can be kind of thought as the same thing. Treat it, you know, like that sort of category, because it's trying to convey that there's a low, it's not a high probability, because we reserve that for the FM line, right? And so it's a low probability of something happening. And the Weather Service is limited in what they can do, because you can only use a Prop 30 when you have some sort of precipitation. You can't Prop 30, as much as I kick and scream over this. You can't Prop 30 winds. Unfortunately, I wish you could. I would be Prop 30ing winds at multiple airports in the Intermountain West every day. Denver would love that. Denver would absolutely love that. But yeah, so the Prop 30, I think as a pilot, you guys should look at it as like a tempo, don't disregard it. It's trying to convey that there's a low probability of something happening and that you need to mentally prepare yourself and brief yourself for that low probability scenario.
Right. Thank you so much. About the one last thing about the mountain wave that you mentioned at the end. Uh, I like to compliment you because that was very well explained and very well said. What we have down here in the below the equator is when we cross the Andes from to Brazil to Chile, and then you cross the area. And that I don't experience once. I experienced only once. I've been flying the 737 for 14 and a half years. I experienced once, and it really got me on edge. It really is scary.
Yeah, and like I said, that's why the NTSB, at least in the US, is so concerned about it that they actually wrote a letter to the FAA saying, "Hey, we need to do something about this." And so, for the Western Arctics, it's a big deal. It's a very big deal.
Thank you so much.
Perfect. Thanks for the question, Spot. If anyone else has any questions to ask, please request to speak, raise your hand, and we will approve it. Evan asks, or he comments, so I hear you like Denver and their weather.
Yeah, Denver. I mean, okay, so I didn't talk about it too much, but one of the things I've been working on my administrative shifts that I have over there is creating climatologies of in particular SIGMETs and non-convective SIGMETs and SIGMETs, because we have climatologies for where for airports, like for the METARs and stuff like that, right? The Weather Service doesn't really have climatologies for, turbulence aloft in the atmosphere or icing or anything like that. And so, especially because you talk about the FAA with their PIREP solicitation and stuff like that, there's a problem with the FAA, and it's not necessarily the FAA's fault, actually, because what's the proper way to phrase this? Like, the idea is if a tree falls over in the woods and there's no one around to hear it, right? Did it really fall type thing? Well, icing, turbulence, and all that stuff is the same deal, right? If there's no airplanes in the mid-levels to report turbulence, how are we going to get a PIREP off of turbulence and stuff like that? And so, I had the idea a couple years ago that like, maybe SIGMETs are probably the better way to go. And so, I've been working for a year and a half on creating climatologies for where SIGMETs are happening and stuff like that. And so you talk about Denver. Denver is the singular ZDV in particular ZDV. ZDV is by far the singular worst Arctic in the country for weather in just, I would guess it's probably in the world, if not, it's certainly in the US, but if not the world type thing. Like, Denver is where bad things happen just consistently, right? Okay, so let's go talk about this slide that I had here. This is that idea, this image right here of the summer C-SIG probability, right? We are firmly centered. There's two maxes here. There's one over northern New Mexico, southern Colorado. It's like 95% every single day during the summer. You are like 95% likely to get a convective SIGMET in that spot. Florida is the other one. Again, it's like 92 or 93%. But again, this is like ZDV, ZAB border right here. We're talking every single day we're getting thunderstorms. And then when you look at the non-convective SIGMETs, Denver is like having turbulence SIGMETs 3 out of every 4 days during the winter. So, and they switch they switch that flip the switch very, very fast, very, very fast in the fall. And so, ZDV is just really, really bad weather all year round. It's Not even close, in my estimation. It's just because of the variety of it. It's not just thunderstorms like Florida has. It's not just turbulence like northern Montana has. It's both. It is really both. And icing is not slouching there either, because you get that freezing drizzle phenomena at Denver Airport where it's like runway 8 is stuck in a quarter-mile visibility, and runway 7 is, 10 and clear because they're above the freezing fog layer. And so, Denver the place is unbelievable in how diverse their weather is and how severe it can be.
All right. Any other questions? Did you want to be here until 8 o'clock, Cameron? 9?
Yeah, if anybody wants to chat after, I'll cut off the stream and we can, or not the stream, but like recording, and we can chat after. But
Sure.
I'll be around till 8,
Okay.
answering any questions anybody has. I hope everybody kind of took away something from this. I know in the last weather seminar we did cover a lot of this kind of thing, a lot of stuff that we talked about. But yeah, I mean, I just wanted to provide kind of my input and then kind of talk about a lot of the AWC products that they have out there and that sort of stuff. So, yeah.
Okay, wonderful. In that case, I guess everyone else is free to go. We do appreciate each and every one of you to being able to attend this seminar. Hopefully, we will be doing these more so in the future. Maybe every quarter is the plan. So please do fill out that feedback form if you can. We do appreciate each and, well, really everything that you have for us. And Cameron's going to be around. Round of applause for him. If you see him around the division, do give him thanks for that. He has done phenomenal in the work that he has done in the last few months, and hopefully he'll be around for another seminar as well in the future.
Yeah. All right.
Thanks.
Mm-hmm.
Okay. Bryn, Jason, anything else to add?
Oh, great job, Cameron.
Yeah.
Thank you. I see we did have somebody requesting to speak.
Yes, greeting. How you guys doing tonight? Can you hear me?
Yep.
Quick question. I just joined, but I am glad that I caught you in the last portion where we were saying about Denver. Using Denver as an example, where you have runway 8 on a quarter-mile visibility in the south side of the airport, clear as a million. Would that be? Let me ask you: is that a factor based on temperature inversions, just temperature differences? What can you what could that be? I'm just curious about it. I'm a former traffic controller, so I'm FAA retired, but
Yeah, so I mean
I worked in South Florida for many years, but that now that you mentioned out of Denver, and that is a problem not only in Denver, but for people that actually fly. For example, I'm born and raised in Puerto Rico. Puerto Rico suffers of something very similar on the West Coast in the summers and the afternoons.
Yeah, and so Denver in particular, you talk about the Denver example. Denver is
Correct.
due to upslope, essentially due to upslope fog. And so what happens is the fog upslopes and then it reaches a point where it just kind of runs out of momentum in its upslope push. And generally that tends to be over the middle of the field. Like, the RVR on 8 will be a quarter of a mile and stuff like that. So that's that particular example for Denver. And the way you diagnose
is
that.
Something seasonal, or is that something that you think is permanent throughout the year?
No. That's mainly a wintertime thing.
Gotcha. Okay.
So, you talk about Puerto Rico and stuff like that. Again, it's the same thing that California's got going on. It's that warm air that's advecting over smaller areas, and then it hits an upslope region, and then it goes up, but then it essentially runs out of momentum and stops. And that's why you get that hard layer there, where once you get above it, it's 10 and clear and everything's fine. But when you go down in it, it's really, really soupy because you're upsloping until you get to a point where the upslope wind can't continue to push upwards anymore because it's ran out of energy.
That makes absolute sense. Thank you so much.
Hmm.
Perfect. Thanks, Jaffa. All right. We do have another question. Tyler, back with a second question. Will a copy of the slides be available later, or just the recording?
I can make the slides available. I think Ashar has them, and we'll have them available for everybody. I should be able to available for everybody to look at.
Okay, perfect. And then another question from Spot. Cameron, can you suggest an application for aviators to monitor weather systems? I use Windy, and I'd be interested in your suggestion.
Yeah, so Windy's a good website to keep an eye on. If you talk about free websites, that's certainly, I think, probably about the best one. Obviously, you have aviationweather.gov, right? They do the significant weather forecast for the entire globe, both them and UKMet, based in Essex there in the UK, collaborate on that product. And so, you can gain a lot of information like that. But Windy is a really good user-friendly, user-intuitive product to look at for that sort of things. Obviously, right, as a professional pilot, your understanding of weather is a lot more than, I would say even the simmer has on that. And so you can understand a lot of what Windy's trying to do and stuff like that. Outside of that, there's other websites. Tropical Tidbits is another very, very popular one. I love that website. I've loved that website since I was in, and this is what Tropical Tidbits looks like for those of you who don't know. This is the models page, but you can change your region to be almost anywhere in the world. Again, it does a lot of the same things that kind of Windy does because a lot of the same data sources. Let's change it up. We'll go to South America to look at how things move down there. But you can look at this. It doesn't draw out fronts or anything like that, but you're looking at precipitation, surface pressure right here on this sort of map right here. And so, there's other websites that are out there like this as well. The other software I would say is BuffKit. Again, you do have to use BuffKit. You really do have to be familiar with your SKU-T model and using the SKU-T graph. Again, I would say professional pilots probably a little bit more adept at using that than most of the other people out there. But BuffKit is for the U.S. For meteorologists is nearly universal. Not just Weather Service using it. Every single commercial provider and everything like that is using BuffKit in some way, shape, or form to do forecasting. So BuffKit is another very, very good tool. I think if you just Google BuffKit, I think it comes up top. Yeah. So you can distribution and installation is here and that sort of stuff. So like I said, BuffKit is the other, I would say, besides Windy, like nearly universal program that everybody uses. And it's very, very useful for everything. I mean, let's see, I've got BuffKit up here. This is what it looks like on the screen on the application. We'll see if my BuffKit wants to work on this computer or not. It's thinking. Yeah, there it goes. Oh my goodness gracious, -60. We're going to kill that to like -30, so that way it's at least readable. But yeah, so, you can see that it's simulating the SKU-T and what the SKU-T looks like. And so, this is generally what you want to be looking at and that sort of stuff. And then they have an overview view that you look at, shows this. This is my meteorologist setup. Again, your guys is depending on what you're looking at won't be as cluttered and stuff like this. But this view as a meteorologist tells me just so much information that I'm keying up on immediately. So BuffKit is another free and very, very good tool to use. But like I said, you do need to be familiar with your SKU-T diagram and how to use it.
All right. Another question: Why do a lot of FA products include Canadian airports? Maybe you have an answer for that.
What do we mean FAA products include FAA ports like aviationweather.gov?
The one cited here is the NAS status page on the FAA website.
Yes. Okay, so let's talk about NAS status because the FAA works hand in hand with NAV Canada for doing things. So right now, because everything's connected, that's the best way I can explain it. Everything is connected, right? So NAV Canada's ability is let's take this ground delay program at Calgary today, for example. NAV Canada's ability to limit Calgary's let's see here, airport demand. I would guess Calgary's in here. NAV Canada's ability to limit traffic into Calgary is limited because probably about half their traffic is coming from the States. And so the FAA and NAV Canada both work together to come up with ground delay programs and stuff like that for Canadian airports. So you can see here, the reason that they have a ground delay program is because they're pushing all this traffic back into the 04Z hour. And so, you know, that's why NAV Canada is doing that on NAS status NAS status and stuff like that, because they actually can't mitigate the volume all by themselves. They need the FAA to help themselves. And certainly you look at the FAA too, like, you know, the Montreal, Toronto to like New York traffic is not a small number either. So like, you know, if the FAA didn't limit what NAV Canada was doing, you know, their ability would be hampered to limit traffic into New York markets and stuff like that as well. So it's a two-way street, and they cooperate on this sort of stuff. Meteorologically, it's interesting because legally, when we talk about the TCF, of course, this does not apply at all to, you know, Delta or any of the private providers and stuff like that, for the most part. But like, right, there is this TCF area up here in Canada that the Canadian Meteorological Agency will do stuff on the TCF for. And again, it's because everybody needs to work together within the system. Like, it's not just our system, it's also Canada's system as well. Everything works together. Everything works in unison. It's not two separate entities. It's working in unison, presenting the same message. You know, like I said, that social science stuff I talked about plays into this as well. Yeah, and the FAA's data is replicated on the Canadian equivalent as well. So, so yeah, I mean, it's you know, our airspace system is in a lot of ways like Europe's. Everything is connected.
All right, that is the questions so far. I think that's all we have. Unless anyone else has questions, make a final call.
See somebody typing. Thank you. So, yeah, I mean, if you guys ever see me on the network, feel free to reach out, ask questions. I'm always more than happy to help. Like I said at the very beginning, right? This network, VATUSA, has been absolutely instrumental to get me where I am. I can't put a price on what this network has provided to me, you know, not just in my professional career too, but like personal career, you know, all that sort of stuff. These connections that I've made through the network are hugely important. You know, aviation is, you for those of you who are going through the aviation career path right now, I know, Evan, you're going through it. I'm sure there's others that are in here as well. You know, the aviation community is a small community. You know, these people that you're going to flight school with, that you're going to, you know, your class with at your airline and stuff like that, that you're going to the academy with, you know, these are people that you are going to be working with in your throughout your entire career. And so these connections that we make on VATUSA, on VATSIM, are really, really important. You know, just as an example, I mean, obviously I know a lot of controllers that I've been with on my time here, you know, Minneapolis, Towers in Iowa, There's even some that are, moving towards command center and stuff like that. Like, there's a lot of people you meet on the network, and the importance of these connections that you make can't be understated. In my opinion, the network has undoubtedly been a great thing, as frustrating as it can be at times, but yeah.
All right. I am going to end the recording here. Once again, thanks, Cameron.
Mm-hmm.